So how do we calculate the area underneath a curve? Um, well, here it is. Here's the result we're going to be using. The area under the positive curve f at x from a to x can be calculated using the area function a at x is equal to now uppercase f at x minus uppercase f at a, where this uppercase f at x is the antiderivative of f at x. So positive curve f at x, what that means is that the curve is above the x-axis, so these are all positive y values. And the area bounded to the left by some a, that's fixed, to the right here, some x value, the area underneath the curve bounded above and below, here is a at x. So this is a great result that we can use, and we'll be using it a lot, but where does it come from? And we're going to be exploring that in the next few slides. Uh, but before we do that, just quickly, if we had a is equal to 1 and x was equal to 5, we would use this here. Now we don't know what f at x here, but it would be, but a at 5 would equal f at 5 subtract f at 1. So that's what it would look like, at least the first step. Okay, so we have a simple example here where we want to come up with an area function that calculates the area below the straight line y equals 2x plus 1 from 1 to some x value here. And it's a simple example because we don't need to use calculus. We don't need to use the result on the previous slide. We can just figure this out with the area of a trapezoid, because that's what we have here. This is a trapezoid here. So we recall the formula. The formula for a trapezoid is height divided by 2 and then multiplied by the sum of the two parallel sides. So we'll call that A and B. Now going back to our diagram here. H is the distance between the two parallel sides. So H in this example is the distance from R to S, which is from 1 to x. So that distance is the difference between x and 1. So we'll write that down, x minus 1 divided by 2. Now A is this distance here from Q to R, and that's just going to be the y value of Q. So the y value Q is this 2x plus 1, but we have to substitute 1 in there. So let's do that. 2 times 1 plus 1. So that's this distance here. And then we have to add b. Now b is this side here from P to S, which is just the y value of P. Now we don't know, we don't have a number for x, so the best we can do right now is just put 2x plus 1. Okay, so let's keep on going here. Let's simplify. We have 2 plus 1 is 3, and plus 1 is 4. So let's write it now as 2x plus 4. And don't forget to divide by 2. We have a common factor of 2 here, so let's factor out a 2, and let's write it in the front here. Okay, so we have 2 up here and 2 down there. We'll divide it out, and we'll be left with the product of these two binomials, and let's FOIL that out. Let's expand. So x times x is x squared plus 2x minus x minus 2. And one more step here. We have like terms here. So x squared plus x minus 2. So there you have it. We have our area function. And we didn't use any calculus ideas here. but we have an expression here so we can calculate the area. If we knew what x was, we just plug it in and get our area here. So let's look closely at this expression here and focus in on this part here, x squared plus x. If we go back up to the original here, we have the line y equals 2x plus 1. The antiderivative of 2x is x squared, and we have that here in our expression. And the antiderivative of 1 is x, and we also have that. So that gives us a clue that the result on the previous slide, that the antiderivatives have something to do with this process of calculating the area beneath a curve. Okay, so let's go back to our result here. We can calculate the area beneath a curve f at x, provided it's positive, by using this formula here. It's f at x minus f at a, where f at x is the antiderivative of the curve f at x. So we have a diagram here. We have our region here, as we did in the first slide. But I extended the region a bit here by h. So this gray area here is the extension to x plus h here. And we're going to use this diagram to help us understand where this formula comes from. So first off, let's just recall the definition of the derivative of any function and apply it to a. So the derivative of a is equal to the limit as h approaches 0 of a x plus h minus a at x divided by h. Definition of any function. Now, let's take a close look at this numerator. And let's look at our diagram. The area of x plus h is the area starting from a all the way up to here, x plus h. So we're looking at this region here, which includes this and this. And then we're subtracting out the area x, a at x, which is this red region here. Well, if we subtract the two, what we get is this gray region. And let's call that the that region, let's call it the area PQRS. So this gray region here, PQRS, is approximately equal to, well, I drew a trapezoid here, PQRS, that's a trapezoid. This area here, the gray region, is almost the same as the area of the trapezoid. The trapezoid is a little bit more because there's this extra space here. So it's approximately equal to that. So let's write down the area of the trapezoid PQRS. So that would be height divided by 2, right? The distance from here to here will be h. And then we have this side here, PS, which is just the y value of f at x there, right? Plus this distance here from Q to R, and that's just the y value here, f at x plus h. Okay, so these two areas are almost the same. Well, are they ever equal? Well, as h approaches 0, what happens is these two areas approach each other. This is going to be a better estimate of this area as we shrink this as h goes to 0. And it'll actually be equal when h approaches 0 really close, in the limits we say. So we're going to use this fact here when we go back to our derivative. Okay, so we have equality at the limit as h approaches 0. So going back here, And that's what we have here. We have the limit as h approaches 0 of this difference here, and this is the gray region. So we're going to replace this numerator with this expression here. So let me write that out. So I'll just rewrite f at x plus f at x plus h, right? And I can't forget to divide by h here, so I'm just going to write it to the side here. Multiplied by 1 over h. Okay, so we have this. Now let's simplify this. Of h divided by h is 1. So now we can actually just substitute 0 for h here because h has been eliminated from the denominator. And what do we get? We get f at x plus f at x plus 0 all over 2. And f at x plus f at x plus 0, well, this is the same as f at x. So f at x plus f at x is 2f at x. Don't forget to divide by 2, and 2 divided by 2, here we go, we're left with just f at x. So we started with the derivative of a at x, and we ended up with f at x. So let's write that down. Therefore, a prime at x is equal to f at x. Okay, so we have our result here. Now, if we take the antiderivative of both sides here, the antiderivative here is just a at x. And the antiderivative of this is uppercase f at x plus c. So we're almost there. We almost have the result we wanted. The only thing left is, and the only thing missing is this minus f at a. And I'm going to show you how this c value is equal to a negative f at a. Okay, so let's substitute a in here. What do we get? A at little a is equal to f at a plus c. Okay, but what's this area equal to? Well, we'll go back up to our diagram here. We're going from A to A, and that's not a region at all. That area is going to equal 0. So if we were to isolate C, we get C is equal to negative f at a. And there you have it. We go back up here, and we get our result. A at x is equal to f at x minus minus f at a. So we have our result, and we have kind of a proof here where that result comes from. So in the next part of this video lesson, we're going to go through some examples.